Let's do 3.97. All right, so in this case, a rod of diameter 25 millimeters, thermal conductivity of 60 watts per meters Kelvin, protrudes normally from a furnace wall that is at 200 degrees Celsius and is covered by insulation of thickness 200 millimeters. The rod is welded to the furnace wall and is used as a hanger for supporting instrumentation cables. To avoid damaging the cables, the temperature of the rod at its exposed surface, TO, must be maintained below a specified operating limit of Tmax 100 degrees Celsius. The ambient air temperature is T infinity 25 degrees Celsius, and the convection coefficient is 15 watts per meter squared Kelvin. All right, so then derive an expression for the exposed surface temperature TO as a function of the prescribed thermal and geometrical parameters. The rod has an exposed length LO and its tip is well insulated. Okay, so we're given a rod. It has a diameter of 0.025 meters. Has a thermal conductivity of 60 watts per meters Kelvin. The temperature of the wall is 200 degrees Celsius. The length of the insulation is 0.2 meters. The exposed surface has a temperature TO, which has a Tmax of 100 degrees Celsius. We have T infinity of 25 degrees Celsius and H of 15 watts per meter squared Kelvin of the air. They want us to find part A, an expression to solve for TO, the exposed length is LO. And then part B, LO is 0.2 meters. What is TO? And what would you change? Looking at a schematic. So here's our furnace. Oops, let's label it blue. Our furnace wall. Okay, so that temperature T wall is right here. And then we have insulation. And this is that TO point. And we have T infinity and H. another length of our insulation. And here's that length, LO. And then this is diameter. All right, so we have this is our schematic, right? So where do we begin?
Do you make a thermal circuit?
Yes. Yeah, so that's the best approach in this problem, because we have this insulation, right? So we'll talk about what's the best way to approach that. Okay, so let's draw a thermal circuit, okay? So with the thermal circuit, how many resistors do we have? All right, let's step back for a second on this then. What's going on between TW and TO?
Is the insulation preventing any heat loss between those 2 points?
Not any heat. It's preventing any heat to the insulation. So, because if there was no heat loss between those 2 points, TO would be equal to TW, right? So we still have heat transfer between those 2 points, but there's no convection going on, right? Because that's where the insulation is where there'd be convection. Right? So how then, if there's no convection going on, how do we treat, or how do we look at the heat transfer between those 2 points?
It's conduction between those 2 points.
Yeah, so it's purely conduction. There's no conduction convection going on. It's not even, you don't really have to think of it as a fin. Okay, it's just conduction in 1D. There's no combined conduction convection of a fin. All right, so that takes us as one resistor. So we add temperature of the wall, TO, and then we have our conduction. Okay. And then we have from TO now onwards, how many resistors do we have there?
Would it be 2, one for the conduction, one for the convection?
No, so now this is a combined, now this part is a fin, right? So now this is a combined conduction and convection that are not separable, okay? So this is the new part. So this is just a single resistor. And that resistance is the resistance of a fin. Okay, so this already takes into account the combined conduction and convection. So we can't look at a fin as two separate resistors, okay? Because it isn't resisting conduction here, and then there's a different temperature here that has convection. All along the surface, as the temperature is conducting, there's convection going on. So it's a combined conduction-convection. So we have to look at it how we did in the slides when we were talking about a single fin. We have just one resistor from that temperature of the base to the T infinity. All right. So that means that's T infinity. Okay, so the common mistake I do see is separating these into two resistors of one in conduction and convection, and it's not. Okay, so just try to understand that one. All right. We have our thermal circuit. Where is our heat going in this one?
From the wall to the surroundings.
Yep. Okay, so we have then our heat going from the wall, right? It conducts to TO because we have the insulation making it just conduction through there. And then from TO to T infinity, we have the combined conduction convection going on. So we have our resistance of our fin. Okay. And then I think this is where the last class ended. So unless you have any questions, I'm going to stop here. Okay. Any questions? Okay. Well, then that's it for our beautiful Wednesday class, and we'll meet again on Monday.
Thanks, Professor.
Yep, thank you.
Professor?
Yes.
I have a question about one of the homework stuff. Can I ask her on the office thing? The office?
Yeah. So I'll close this, and then we can go right into the office, our
Perfect.
channel.